It's raining outside and I'm feeling great. My mind and body is at peace. There's no net external force acting on me right now. Are you in equilibrium? From where did you hear this term? I watch all your videos. See, equilibrium of a body not only requires the translational equilibrium, wherein we say that the net external force acting on the body is zero, but it also requires rotational equilibrium, wherein net external torque acting on the body is also zero. You never support any of my statements. See, I supported, but I added something to that. Like, I love my sister although she is terrible. What? I supported you and added something to that. इतना दिमाग तुम पढ़ाई में क्यों नहीं लगाती? तुम क्या करोगे फिर? Do you talk like this to your elders as well? You are special. Roots need breathing space. And if the net external force acting on the body is zero, then from Newton's first law of motion, I can say that the particle is either at rest or in uniform motion. So if there are two forces acting on a particle, equilibrium of that particle requires that the two forces, say F1 and F2, must be equal and opposite. You know, force is a vector, so the condition of equilibrium of a particle on which two forces are acting is this. The two forces are equal in magnitude but opposite in direction. If this condition is satisfied, then we say that under the action of two forces, the particle is in equilibrium. Wow! What if I have three forces acting on a particle? The concurrent forces. So equilibrium under the action of three forces requires that the vector sum of all these three forces should be zero. And how do we write this? F1 plus F2 plus F3 is zero. So this is the condition wherein three forces are acting on a particle and the particle is in equilibrium. This condition has to be satisfied. Now, do you understand what this means? Force is a vector, so they have direction, magnitude, and they add according to triangle law of addition, triangle or the parallelogram law of addition, whichever you understand. So what does this mean? So if I have x, y and z directions, this coordinate system, this means this. इनको ऐड कैसे करेंगे? How do we add these forces? Simplify the things. Choose one direction at a time. Let us talk about x direction and then take the components of all these three forces in the x direction. जो भी इनके components आएंगे x direction में, सबसे पहले वो zero. So this is what I have written. Next step is to check the components in the y direction. Again this. And finally in the z direction. So this equation actually means this, this and this. ठीक है? So equilibrium under two forces implies this condition, that is, if I am having one force, say F1 in this direction, the other force F2 will be equal to this F1. I've drawn the same length to denote the equality, but the direction of F2 will be opposite to that of force F1. Okay? Now when I talk about equilibrium under three forces, I write down this: F1 plus F2 plus F3 is zero. So what does that mean? First of all, I'll be taking the force F1. First of all, I'll be taking the force F1 and another force, say F2, which can be along this direction. Now, how do I add these two forces? I complete the parallelogram like this, and the resultant will be this diagonal. So this is the resultant. I denote it by R, say. ठीक है? So equilibrium under the action of three forces implies this. So what do I conclude? For the equilibrium of three forces, this third force, that is F3, must be equal and opposite to this force R, to the resultant R of the two forces, like this. This is my F3. Now if I forget about this resultant, what do I get? So this is the arrangement of three forces which are acting on some point or a particle, say A, and A is in equilibrium. Another thing that you know is parallel translation of a vector does not bring about any change in it. So let me do parallel translation for these vectors. Let F1 remain at the same position. I am picking this force F3 and moving it parallel to itself so that it comes here. And F2 is this. So I will be translating this force so that it comes here. So what will I get? I will get something like this, I guess. F1, F2 and F3. From this to this. You can check the direction of my arrows. I have translated this force F2 parallel to itself so that it comes to a position here. The tail of force F2 coincides with the head of force F1. पहले कहीं और थी, अब किसी और जगह चल पड़ी, पर है वो फोर्स F2 ही. ऐसा करने से कुछ चेंज नहीं हुआ. जो प्रॉपर्टीज़ उसको फोर्स F2 बनाती थी, अब भी वही प्रॉपर्टीज़ उसको फोर्स F2 बनाए रख रही हैं. जस्ट मैंने उसका पैरेलल ट्रांसलेशन किया है, दैट्स इट. सिमिलरली द फोर्स F3 वाज देयर. F3 को मैंने सिंपली थोड़ा सा बैकवर्ड्स मूव किया है along this line only so that the head of F3 coincides with the tail of F1, and I will be getting this. So what do you conclude from this? Three forces in equilibrium can be represented by three sides of a triangle with vector arrows taken in the same sense, which means that at all three corners, if you check, so you can check this for all three corners of this triangle, the head of one vector is coinciding with the tail of the other vector. दो tails नहीं coincide करी, दो heads नहीं coincide कर रहे. At every corner, the head and the tail are coinciding. Now this thing can be generalized to n number of such forces. For example, if I have F1, F2 up to Fn number of forces, a particle is said to be in equilibrium under the action of these n number of forces if these n forces can be represented by the sides of a closed n-sided polygon. इसको देखो, ये कोई n sides का, n number of sides का एक closed polygon है. मुझे बनाना नहीं आता, मेरा खुला हुआ लग रहा है. ठीक है? With arrows directed in the same sense. This is important. With arrows directed in the same sense. If you check each corner, the head of one vector will be coinciding with the tail of the other. No two heads, no two tails. तो equilibrium ये कहता है. The roots of a tree need breathing space and place to grow. An environmentalist says that cemented structures close to the tree trunk can choke its roots. Can we apply this to human beings as well? So I hope you liked this video. If you do not forget to give it a big thumbs up, and I'll be back with my next video. Till that time, do not forget to take really good care of yourselves.